Good morning, students. So in this particular video session we will be discussing about the next part of the perspective projections, such as the perspective projection view volume. So what do you mean by frustum in case of perspective projections? So what do you mean by symmetric frustum? What do you mean by oblique frustum, and so on? So these are the topics we will be discussing in this particular video session. So perspective projection view volume. Okay, till now we have discussed the view volume related to the orthogonal projections or the orthographic projection. So let us try to understand what is the shape of the perspective projection view volume. A perspective projection view volume is often referred to as a pyramid of vision because it approximates the cone of vision of our eyes or a camera. So this perspective vision view volume is based upon how a human eye or a camera looks at the world or looks at a given scene, right? Our human eye, it is not uh, it's basically restricted to a given field of view. The peripheral, including the peripheral vision, the field of view of human eye is around 128 degrees. So whatever objects that are lying beyond this angle cannot be captured by the human eyes until we move the head or until we turn the heads, right? So that is what is the concept behind this particular projection perspective or perspective projection view volume here. So if you remember in the orthographic projection, what was the shape of the view volume? So in case of orthographic projection, the shape of the view volume was a rectangular parallelepiped. Okay, the orthogonal view volume, the shape was kind of a box, right? We call it as a rectangular parallelepiped. But here, the shape of the perspective projection view volume will be of the form of a pyramid or a truncated pyramid, as we can call it. Okay, so if we consider this projection reference point, this far clipping plane will act as a base of the pyramid. Okay, now if we restrict the z-axis to the near and the far clipping plane, we get a truncated pyramid, or we call this particular shape as the frustum. Okay, remember, in case of perspective projection view volume, the shape of the view volume will be in the form of a rectangular frustum. What do you mean by rectangular frustum? It is basically a truncated pyramid. The top of the pyramid will be removed, right? You have one base of the pyramid which is larger, and the top of the pyramid will have one more rectangle which is smaller. Now why there is a difference in the two dimension? That is because the projection paths are going to convert this particular projection reference point. Okay, so we can place the view plane here, and then we have two more planes, the near clipping plane and the far clipping plane. This shape that we have here, okay, that is what we call as a frustum. So this is shape. It is basically a pyramid which is truncated at the top. Okay, so we have the near clipping plane and the far clipping plane which are used to truncate the pyramid. So remember, the shape of the perspective projection view volume is called as the rectangular frustum. We call that particular view volume as the rectangular frustum view volume. So what do you mean by a frustum shape? It is a pyramid, or we can call it as a truncated pyramid. Okay, the clipping window will be placed here, and this will be the projection reference point. So this particular frustum is based upon the, or it approximates the cone of vision of the human eye. How does a human eye perceive the given scene? How does a camera look at a given scene? So there is a particular angle or particular field of view for a given camera lens. If you want to capture more, we need to change the lens to wide angle lens and so on. So depending upon what is the field of view, so we can actually decide this particular frustum for a given perspective projection view volume. So remember, the shape of this perspective projection view volume is a rectangular frustum. Now, we can use a three-dimensional homogeneous coordinate representation to express the perspective projection equations in the form given as xp is equal to xh divided by h, and yp is given as yh by h. What is this xp and yp? It is the position of the point on the given projection plane. Okay, if I have one projection here, so the coordinates on the view plane, we are representing them as xp and yp, The equation for xp and yp using the homogeneous representation is xp is given as xh divided by h and yp is given as yh divided by h, where the homogeneous parameters are calculated as follows. The homogeneous coordinate h is given as the difference between the z coordinate of the projection reference point and the z coordinate of a given point. Okay, so the homogeneous coordinate h is given as the distance between the z coordinate of the projection reference point, this point, z coordinate of the projection reference point, and the z coordinate of a given point that we are going to project. Okay, so every point here it is given as x comma y comma z. So similarly, the point at the projection reference point, it is represented by x prp comma y prp comma z prp. So the x comma y comma z. So the value of this homogeneous coordinator h that is used in this particular equation, it is given as the difference between the z coordinates of the projection reference point and the z coordinate of the actual point which needs to be projected. And also they have given us the equation for xh and yh, which acts as the numerators for calculating the values of xp and yp. Xh is given as x into the difference between the z coordinate of the projection reference point and the z coordinate of the view plane. So zprp minus zvp plus xprp, that is the x coordinate of the projection reference point, into zvp minus z. So this equation will give us the value for xh, which can then be used to calculate the value of xp. To calculate this, what do we need? We need to get the value for x comma y comma z. We need to get the value for xprp, yprp, zprp, and we also need to get the value for zvp. If you're having these many values, you can compute the value of h equals to zprp minus z. Xh is given as x into zprp minus zvp plus xprp into zvp minus z, and yh is given as y into zprp minus zvp plus yprp into zvp minus z. In case of xh, you have x and xprp. In case of yh, you have the coordinate y and the y coordinate of the projection reference point. These are the equations for computing the xh and yh, and this is the equation for computing the h. Both these equations can be used to compute the value of xp. Similarly, the equation of yh can be used to compute the value for yp, right? So this is the homogeneous coordinate representation to express the perspective projection, right? Now, the perspective projection transformation of the weaving coordinate position will be accomplished in two steps. So there are two steps to perform the perspective projection transformation of a weaving coordinate position. So if you remember the three-dimensional weaving pipeline, so one of the phases or one of the stages of the pipeline was, so from the modeling coordinates we converted to the world coordinates. From the world coordinates we transformed to the weaving coordinates. The next step was to transform from the weaving coordinate to the projection coordinate. That is what we are talking about here. Converting from the weaving coordinates to the perspective projection coordinates is accomplished using two steps. Okay, the transformation involves two steps. First, we have to calculate the homogeneous coordinates using the perspective transformation matrix. So the transformation sequence is represented by ph equals to m perspective dot p, or m perspective into p, where ph is a column matrix representation of the homogeneous point xh comma yh comma zh comma h, and p is a column matrix representation of the coordinate position x comma y comma z. So ph is given by xh comma yh comma zh comma h, and the matrix p is a column matrix which is given by x comma y comma z comma 1. The perspective matrix is given something like this: m perspective is equals to, so the first element in the first column is zprp minus zvp, z coordinate of the projection reference point minus z coordinate of the view plane. So second element of the first row will be 0, third element of the first row will be minus xprp, right? Minus xprp, which is the x coordinate of the projection reference point, and the fourth element of the first row will be xprp into zprp. Similarly, second row we have the first element equals to 0, The second element in the second row will be ZPRP minus ZVP. The third element in the second row will be minus YPRP, and the fourth element in the second row will be the product of YBRP into ZPRP. Similarly, third row we have 0, 0, and we have two terms here. What are these two terms? SZ and TZ. What are these? These are the scaling and translation factors along the z-axis. Z is a scaling factor along the z-axis, and Tz is a translation term along the z-axis, or a translation parameter along the z-axis. And the last row of this matrix will be represented by 0, 0, minus 1 ZPR. So this is the perspective transformation matrix, which is used to calculate the homogeneous point xh, yh, zh, h, which is again a column matrix, as a product of this perspective matrix into a given coordinate position. So every coordinate in the weaving coordinates should be transformed to the projection coordinates by using this transformation. We have just looked into one point here. There may be multiple points that form a given 3D object. So every point should be transformed in this particular way. That is the first step to calculate the homogeneous coordinates using the perspective transformation matrix. So this was the perspective transformation matrix with which we multiplied the given coordinate position in order to calculate the column matrix representation of a homogeneous point PH. Okay. Now, before proceeding further, let us try to understand what do we mean by symmetric perspective projection frustum. Okay. Now, if you look at this particular diagram here, again, you have the perspective or the projection reference point XPRP, YPRP, ZPRP. You have the view plane here. This is the position of the view plane. Here, ZVP is the position of the view plane. And this is the view of the frustum from the top. If you look at a given frustum from the top, this is how it looks like. So you have the near clipping frame or the near clipping plane and the far clipping plane. Now, if you have a line of projection, okay, if there is a line of projection that passes through the view planes, okay, so if you have a projection line, so line from the projection reference point through the center of the clipping window and onto the view volume, so we call it as a center line, right? This is the frustum center line here. So the line from the projection reference point, that is this point, through the center of the clipping window and on through the view volume is a center for a perspective projection frustum. Now, if this particular center line is perpendicular to the view plane, we call it as a symmetric frustum. Okay, if it is perpendicular to the view plane, this is the view plane here, we call it as the symmetric perspective projection frustum. Why the word symmetric? It exactly divides, or it exactly splits the frustum into two parts. Do you observe that? If I have a frustum center line something like this, it exactly splits the frustum into two parts. Hence, it is called as a symmetric perspective projection frustum. Okay, if the line from the projection reference point through the center of the clipping window and through the view volume is perpendicular to the view plane, we call it as a symmetric frustum. So what is a frustum? The line from the projection reference point through the center of the clipping window and on through the view volume. This is a center line for the perspective projection frustum. And if it is perpendicular to a given view volume, we call it as a symmetric projection or perspective projection frustum. So why is it called a symmetric perspective projection frustum? It splits the frustum into two symmetric parts. Okay. Now, these are the terms or these are the equations we have to compute the coordinates or the boundaries for the clipping window in case of a symmetric perspective projection frustum. So this will be our clipping window, or this will be the clipping window, the view plane. So what are the coordinates or the boundaries for that? That is specified here. So XW minimum is given as XPRP minus the width of the window divided by 2. XW max is given as XPRP plus the width of the window divided by 2. YW minimum is given as YPRP minus height by 2, and YW max is given as YPRP plus height by 2. So if you know the window width and window height and the projection reference coordinates XPRP and YPRP, we can calculate the boundaries for the left, right, bottom and top of a given clipping window in case of a symmetric perspective projection frustum. Now, so in computer graphics, the cone of vision is approximated with a symmetric frustum, and we can use the field of view angle to specify the angular size for the frustum. Just like what we discussed earlier, our human eyes is capable of capturing up to 120 degrees of vision, including the peripheral visions. So beyond that, whatever objects are there, we cannot see until we move the head. If a head is fixed and if eyes are fixed, if the eyes are fixed to one particular position, we can view up to 120 degrees, including the peripheral visions. So there is some angular limit for what can be captured by the human eyes. Similarly, we can also set an angular size for the frustum to decide what are the things that the frustum is going to capture or the clipping window is going to capture. You can see here theta is given here. So this is called as a field of view angle. So depending upon the field of view angle, we can determine how many or what is the part of the scene that will be captured by a given uh, projection reference point or by a given frustum or by a given symmetric projective perspective or perspective projection frustum over here, right? So we have the projection reference point, again we have the frustum, we have the clipping window, but here we have one more thing called as the field of view angle that determines how much of a given scene are you going to capture or how much of a given scene is a particular frustum view volume going to capture. Anything that is beyond the field of view will be clipped by this clipping window. Okay, anything that is beyond the field of view angle will be clipped by the clipping window, and that will not be projected onto the view window or the viewing view plane over there. Okay, that is about the field of view angle. Now, if the center line passes through the projective view volume is not perpendicular to the view plane, we have an oblique frustum. See, we have something called the symmetric frustum, which we discussed just now. Here, the center line from the projection reference point passes through the view plane and through the view volume. If it is perpendicular to the view plane, we call it as the frustum center line, right? Now, there is one more frustum called as the oblique perspective projection frustum. In simple words, oblique projection perspective or the perspective projection frustum is a frustum which is not a symmetric perspective projection frustum. Any perspective projection frustum which is not a symmetric perspective projection frustum, we can categorize it as an oblique perspective projection frustum. So what do you mean by that? If the center line of the perspective projection view volume is not perpendicular to the view plane, as you can see here, this angle is not 90 degree. I mean this angle, the angle between the center line and the view plane. If it is not perpendicular to the view plane, then we have an oblique frustum. So in simple words, any non-symmetric perspective projection frustum can be categorized as an oblique frustum. So where the center line of a projective perspective view volume is not perpendicular to the view plane. That is what we call as the oblique perspective projection frustum. Now, taking the projection reference point as the origin, that is xprp, yprp, zprp equals to 0, 0, 0, we obtain the elements of the required shearing matrix as m z shear is given as 1 0 sh zx 0 0 1 h zx zy 0 0 0 1 0 and 0 0 0 1. So we need to basically convert the we need to apply the shearing to convert an oblique perspective projection frustum to a symmetric perspective projection frustum before we can process the coordinates or before we can apply the transformation to the coordinates. We need to first apply the shearing transformation. What does shearing transformation do? It basically stretches a given object in a particular direction. In this case, we are applying the shearing along the z-axis. So taking the projection reference point as xprp, yprp, zprp equals to origin. So we obtain the elements of the required shearing matrix as mz shear is given as 1 0 shearing factor along x-axis, zx 0 0 1 sh zy 0 0 0 1 0 and 0 0 0 1. So then we need to choose the values for the shearing parameters such as such that 0 0 z near 1 is equal to this matrix, that is mz shear, into the column matrix which is given as the sum of the left and right values by 2. Second element is the sum of the bottom and top values divided by 2, z near and 1. So this is going to give us the values for the z near. Okay, or this is going to let us choose the values for the shearing parameter. So 0 comma 0 comma z near comma 1 0 0 z near 1. This is a column matrix which is obtained by the product of this particular z shear matrix into a column matrix with first two elements can be obtained by adding the sum of the left and the right boundary, that is xw minimum and xw max divided by 2. Similarly, the second element is obtained by finding the sum of the bottom and the top boundaries, that is yw minimum and yw max divided by 2, z near and 1. So therefore, the shearing parameters for this shearing transformations can be given as shzx is given as minus of xw minimum plus xw max by 2 into z near. Similarly, hzy is given as the sum of the bottom and the top boundaries, yw minimum plus yw max divided by 2 into z near and negation of that. So these are the transformations we need to consider for oblique perspective projection frustum. Okay, so we need to consider two more matrices here. M perspective, which is given as minus z near 0 0 0. Second row here is 0 minus z near 0 0. Third row we have is 0 0. Scaling factors along z axis, which we discussed earlier, sz, tz, and 0 0 minus 1 0. So this is the perspective projection matrix that we need to consider, which will be multiplied with this particular matrix that we discussed earlier in order to perform the transformation for an oblique perspective projection frustum. Okay, so the transformation for the oblique perspective projection frustum is given as the product of the perspective matrix, which is given by this into the matrix representing the z shear. If you multiply these two things, this will be the concatenate or the composite matrix that we get. So matrix for oblique perspective projection transformation is given as z near 0 xw minimum plus xw max divided by 2 0 0 minus z near yw minimum plus yw max divided by 2 0 0 0 scaling factors which were used in this matrix sz tz, and the last row will be the same as this matrix 0 0 minus 1 0. That is about the transformation that is applied in case of an oblique perspective projection frustum, right? So in today's session we discussed what is the shape of the perspective projection view volume. So what is the shape of the perspective projection view volume? It is in the form of a frustum. So what is a frustum? A frustum is a truncated pyramid which looks something like this. This will be the shape of the perspective projection view volume, where one rectangle will be larger and the other rectangle will be smaller. This is due to the convergence of the projection parts to a projection reference point. This is what we call as a frustum. Now we discussed a bunch of equations for calculating the value of xp and yp, values equations for calculating the value of h, homogeneous parameters xh and yh. We also discussed one transformation sequence for calculating the perspective matrix in case of perspective projection, and we looked into something called what do you mean by symmetric perspective projection frustum. So basically a center line that passes from projection reference point through the center of the view plane and through the view volume, and if this center line is perpendicular to the given view plane, we call it as symmetric perspective projection frustum. These were the equations for calculating the boundaries of the clipping window in case of the symmetric perspective projection frustum. And then we discussed something called as a field of view of a given frustum. Just like a human eye is having a particular cone of vision, a particular field of view angle, even a camera lens, a particular lens will be having a particular field of view. If you want to capture more, we need to use a wide angle lens. The angle theta will be increased. Similarly, we can decide what is the amount of scene that will be captured by a perspective projection view volume by changing the value for the field of view of a given angular sized frustum, right, by altering the value of the theta over here. And then we discussed what do you mean by oblique perspective projection frustum. Any perspective projection frustum that is a non-symmetric perspective projection frustum can be called as an oblique one. Okay, if the center line of a perspective projection view volume is not perpendicular to a view plane, then we have a oblique frustum. Then we discussed a bunch of matrices, right? So for this, I'm going to end today's session.